That's right. Today, we're talking about Heisenberg. So today, I'm going to tell you what the Heisenberg Uncertainty Principle really means and why it really matters. So, like I said before in the episode about the Schrödinger equation, position and momentum are tied together inside of the Schrödinger equation. They're sort of coupled together. And what the Heisenberg Uncertainty Principle says is that the variance in position multiplied by the variance in momentum has to be greater than or equal to the Planck's constant divided by 2. Now, if you remember, Planck's constant is just a number, and that number basically means that you are dealing with quantum mechanics inside of your equation. So, whenever you see Planck's constant, you're in quantum mechanics. Because remember, in quantum mechanics, we don't have position functions or momentum functions, we have wave functions. And the wave function is how we measure a particle's position or momentum, brought to you by the Schrödinger equation, a solution to the Schrödinger equation. And because each wave function is a statistical distribution of position and momentums, that means that there is an inherent uncertainty to every position measurement and every momentum measurement. You can find a very likely spot for a particle to be at, but there is some variance to that. So knowing that in statistics that there is an inherent error to any measurement inside of it, that error is our deviation, or our sigma, basically, for this Heisenberg Uncertainty Principle. The delta, the change in how much a normal distribution will look. And the same thing happens with momentum. Now, momentum isn't explicitly plotted onto the wave function itself. If you solve for a wave function in position space, which I will get to in a future video, the difference between position space and momentum space. So look forward to that and hit subscribe to get ready for that video. But what happens is the momentum is basically the derivative of position. If you remember, momentum equals mass times velocity in classical mechanics. Well, velocity is just the time derivative of a position function. So we have a position wave function. We can just take a time derivative and find the momentum from that. And that's called the momentum operator, acting onto the wave function itself. And the same thing happens. You get a wave function in momentum space, and that wave function, you can measure a definite momentum, but there is some inherent variance to the actual graph itself because it is still a statistical distribution. And now that variance gets multiplied by the variance in position, and the variance in momentum multiplied by the variance in position has to be greater or equal to Planck's constant over 2. Or, well, really Planck's reduced constant over 2, or Planck's constant over 4 pi. Because there are two Planck's constants, actually. There's Planck's reduced constant, which I mostly like to work with because it gets rid of factors of 2 pi. And there's also Planck's constant, which is the default Planck's constant, just h. Planck's reduced constant is h with a bar in it. So if you also remember from the first video, I said that a Moore function of definite momentum won't cross 0 as much. Now what that means is that a function of definite position will be a large spike right in the middle of one spot, and that is the spot of definite position. It's impossible to have, but that is what it is. So that means we know for certain that the position is going to be in that spot where the graph spikes up. But now from Heisenberg's uncertainty principle, if we have 0 variance on the position, that means we must have an infinite variance on momentum. So because we know information about the position of the particle, we have no information of the momentum of the particle. Now, this graph is unrealistic and this solution is unrealistic, but it's a good way to think about it. the more you know about the position of a particle, the less you know about the momentum. And the more you know about the momentum of a particle, the less you know about its position. And I'm going to link here a video from Veritasium that explains this very well and gives a very good demonstration of what it really does when he uses a laser. He uses a laser to measure the position of a particle, and you can see how the momentum changes. So back to the example of the wiggly graph. The more wiggly a graph is, that means it's more of a higher momentum state. And so you can measure the momentum easier. But you don't know the positions as much because the graph is so wiggly. There's spikes in the amplitude periodically, and there are more spikes in the amplitude with the wigglier functions. So that means there's a lot more variance in the position, but there's less variance in the momentum. So long story short is, the more you measure about a particle's position, the less you know about the particle's momentum. And the more you know about the particle's momentum, the less you know about the particle's position. And that rule is dictated by the Heisenberg Uncertainty Principle. But remember, these uncertainty principles are exclusive to quantum mechanics. This is a quantum mechanical phenomena because of the statistical nature of quantum mechanics. Now, there are more philosophical interpretations of Heisenberg's uncertainty principle, like the trade-offs you have to make in certain things, which equate to the trade-offs in measuring a position and momentum. So if you trade off one thing for another, you lose some of the measurements, or at least some of the benefits of the one thing over the other. And we have to do this every single day. We have to make trade-offs, we have to make decisions on what's more important and what we need to get done. Say you decide that you want to study for a test more, and so you spend your entire weekend studying for a test, but you miss your best friend's birthday party. Well, you traded off some uncertainty in your friendship for more certainty in getting a good grade on a test. You're more certain about one thing than the other. And that's another point of Heisenberg's uncertainty principle, or any general uncertainty principle, as a matter of fact. Things have these trade-offs in uncertainty. The more certain you are about one thing, the less certain you are about another thing. That's Heisenberg's uncertainty principle. And it's all about basically measurements and getting these things done. You measure one thing more, then you know less about the other thing. You study more for a test, you know less about other things. I don't know. Or you can be completely uncertain about everything, I guess. I don't know. So to recap, position is a statistical interpretation in quantum mechanics, and so is momentum. Because they are statistical interpretations, there is an inherent variance to them, to each of their measurements. So the more variant position is, the less variant momentum has to be. And the more variant momentum is, the less variant position has to be. And this rule is dictated by Heisenberg's uncertainty principle. And this is what Heisenberg's uncertainty principle really is it's the inherent variance in these two quantities has to be greater than or equal to Planck's constant divided by 4 pi. It's more about the statistical interpretation in physical measurements in quantum mechanics that this uncertainty principle really is what's being talked about. So the next time you hear about Heisenberg or Heisenberg's uncertainty principle, you'll know that what it's really talking about is the measurements and the uncertainty in the measurements that have to be there because of the statistical nature in quantum mechanics. And that's it. Thanks for watching. Hit like and subscribe for future videos, and I will be back with more quantum mechanics later.